pounds divided by the area, 3.976 inch square. Now remember, pounds divided by inch square gives us psi, so that's 5,256.19 psi. Then you can move the decimal places 3 to the left. We get 5.256 ksi in compressions. For stress of car BC, basically perform the same thing. So in this case, I'm just gonna directly plug in the numbers, and we will end up in 11.827 ksi in compressions. Alright, now for determining the deflections at point B, what we're gonna do is looking at our graph. In this case, we know this is steel, this is aluminum, and we know this A is this B, this is A, this is C. So as you can see, the last steel, so we're going to use steel in this case. So it'll be deflection of steel is equal to the deflections minus the deflection of P. So by plug in, we'll get 0.01092 inch minus the P, the force, 2.0846 E287 P inch. And since now we know P, we can plug in P, and we'll get 0.006563 inch, or 6.56 e to the negative 3 inch. As you can see, the sign is positive, and it's getting towards the right. So that actually end up these problems. If you have any problems, feel free to leave in the comment sections and subscribe if you can. See you next time. Hello guys, welcome again to this problem solving stage. So feel free to pause the video and read the problems. And if you did, let's get started. So we have to determine the stress in material A, and we want to specify whatever is tension under pressure, and we're going to need to determine the deflection of point B, and specify left or right. Here's information given the E2. So straight from the beginning for the solution, what do we know? We know that the rod is experiencing several expansions. So it's going to get a rod, and there's a force P that's from back. And we know that all this deflection is between two rods. It's going to end up zeros. So we know this, we can proceed. So for round one, what we're going to have is the deflections caused by the temperature of the first ones minus the deflections caused by the P, the force that's going on this way, to counteract the expansions. Plus the thing for 2 and 3 is going to give us 0. It's going to give us 0. So all we can do now is plug in the formulas. So it'll be exactly the same thing right here. So that, and you just change the and except 1 equal 2 underneath, and except 2 for the third one, even for the third one. So we're basically doing almost the same thing as we did for the last video. Just except 3 terms, we now have 6 terms instead. So you can feel free to simplify this long-term thing right there, and feel free to sub in the values you have. In our case, if I sub in the values I have, I'll end up P is equal to negative 72 kilojoules pounds. Or since this is negative, what we know is this is in the wrong direction, so it'll be pounds and tangents. Because we assume the P goes in the compression of the rod. So P goes this way, this is rough 3, and it goes rough 2 and rough 1. Now we know P. To find the stress in material A, we just gotta apply our stress formula, which is P divided by A. In other words, we're using our P, we just calculate it, which substitute in our P, and divide by area, which is given in the problem. This is 2 inch square. And we're getting 36K pounds over inch square, which is 36K psi, or 36 ksi in tangents. And to find the part B, deflections of point B, we basically do deflection of point B is equal to the deflections caused by the raise of temperature or the close of temperature minus the deflection caused by minus the deflection of the P, the force will apply to the deflections as a change. So after plugging the numbers, it'll be 10 times 10 to the negative 6 of the degrees of F times by negative 100 degree F times 10 inch minus P 10 inch 2 inch square times 10 e of 6 psi. Now, there's a mistake you can make right here about P, because we say is negative 72K for our P. If you plug in the positive 72K, you get wrong answers here. So make sure just stick with the negative before you do anything. So it'll be 0.025 inch and 2.5 e to negative 2 inch to the right. Because it's to the right. Alright, so that solves the problems. If you guys have any problems, feel free to leave in the comment sections. And I'll see you guys next time. Hello guys, welcome. And today we're going to do the volume problems. So feel free to read the problems. And we'll begin right away. So the most inside is our case aluminum, and there's B, brass, and most outside is the stainless steel. And we got force P, force in both directions. Therefore, we're asked to find the normal stress in the press and the deflection of the composite rods, and given the dimensions and equations like that. So, for solutions. Right away, we can find the area of each section. So, under each section is the area of the aluminum portions, the area of the brass portion, and the area of the stainless steel portion. So, we know the area, since we given the diameters, K is equal to I divided by 4, D squared, and for our D1, which is the aluminum, we want 1, we get 0.7854 inch squared as our area. And for cross-section area for up 2, which is our brass, is equal to I over D squared again. However, in this case, the D squared is equal to the D2 squared, which is 2 squared, minus the D1 squared, which is 1 inch squared. Therefore, we got 2.3562 inches squared. And we'll perform the same thing for A3. So, by plugging the numbers, we'll have 3 squared minus the 2 squared, and that's 3.927 inches squared. So that solves the cross-section area for aluminum, brass, and stainless steel. Now, what do we know about the cylindrical extension in this case? We know that the P1 plus P2 plus P3 is equal to P. And we know that the deflections are all equal to each other. Therefore, we can say deflection 1 is equal to deflection 2, and the deflection in this case is PL divided by AA, and that's exactly equal to that. And if you read the problems, we know that they all have the same lengths. Therefore, the lengths can cancel out. And we got a P1 divided by the area, and in this case, 1 is our aluminum, and our 2 is our brass. By plugging in the given inputs, we got 0.754 inches squared. We calculate for A, and for EA, by given is 10 times 10 to the 6 psi, and that's equal to the P2 divided by 2.3562 inches squared. Now we just calculate it times by 15 times 10 to the 6 psi. That's given the problem. And if we solve for P1 in this case, we'll get 0.2222 P2. And based on the general equations we have right here, we can know that the deflection of point of 2, which is brass, is equal to the deflection of the 3, which is the stainless steel. Therefore, we can use the same formulas again, like the one we just did. It will end up being the following. So I'm basically copying exactly for P2 right now, and for P3, we can just use the area right here, which is calculated, and plug in the E, which is 28 e to the 6 psi. So by solving this, and for P2, we know P2 is equal to 0.3214 P23. Okay, now what do we know? We know that the P1 plus P2 plus P3 is equal to P. Therefore, P1 is equal to 0.2222 P2, and P2 is P2, and P3 in terms of P2 will give us 1 over 0.3214 P2, and that's by our problem. The P is 50 kips, which in this case is 50 times 10 to the 3 pounds. So by solving for P2, in this case, P2 is equal to 11537.8 pounds. So we can find the P1 by using 0.2222 times P2. In this case, will end up being 2,563.7 pounds. And P3 can be derived by using a volume which is defined for P2. divided by 0.3217, and that's 35,898.5 pounds. So now we know to find the normal stress, we're just going to apply our stress formulas, which is sigma is equal to P divided by A. And sigma as a press will be sigma press, B press, P press, and A press, which we already know. So P of B is P2, or just calculate, so 11537.8 pounds, divided by area of the press, in our case 2.3562 inches squared, pounds divided by inches squared gives you PSI, so it will be 4,896.78 PSI, or 7.897 KSI in compressions. For the deflections of the composite rod, deflections, we use the deflection formula, which is, in this case, I can just right away, because we know this PL divided by A, which P divided by A is the sigma of B. So this becomes sigma of B and L divided by E of B. So we know that sigma of B, which is calculated, is 4896.78 times the length, 10 in this case inches, divided by the E of B, which by the problem given is 15 times E10 to the 6 PSI. This gives us 0.00365 or 3.265 times 10 to the 3 inches, and that is shorter. So if you have any questions, feel free to leave in the comment sections and subscribe if you can. See you next time. Hello everyone, welcome, and feel free to read the problem, and we'll start right away. So as you can see, this is a temperature change, and as to calculate the stress in aluminum problem. So right away from the given, we can find the area of the core and the area of the shell. So the area of the core is pi over 4 E squared, with B equal to 25 millimeters. This gives us 490.874 millimeter squared. And for A of the shell, pi over 4 D squared, except that D this time is 60 millimeters squared minus 25 millimeters squared. So by plugging the numbers, we get 2,336.56 millimeter squared. And what do we know about the right journal? We know that the deflection of 1 is equal to deflection of 2 is equal to total deflections. And we know how long each of the portion wants to extend out. So we know that the sigma of A is greater than the sigma of S. This proves that the aluminum is getting longer than the steel. Therefore, this is very helpful when we try to calculate this. By plugging our deflection formulas, PL divided by AE plus our deflections, this is the force of heat trying to push back. This is how the material wants to extend. So this equals to PL, this for steel right here is for the aluminum, ASES plus WT length. From here we can cross off the lengths of each side. That's length right here. And we know that P of A is equal to QA of AA. And if we try to solve for the P on there, in our case, it will be for P of A will be sigma A times the area of the aluminum we just calculated, 2,336.56 is equal to sigma of the steel times 49.87 for area of the steel. Therefore, sigma of A is equal to 0.21 sigma of S. I always say aluminum is trying to get longer, and this aluminum is longer than the steel. Therefore, the steel, since they both extend together, we don't want aluminum to get too long, so we'll have a force that makes aluminum the same length as the steel, and we'll have a force that makes the steel the same length as the aluminum. So steel is getting longer and aluminum is getting shorter. Knowing that, we know aluminum is plus, and minus the P that makes aluminum push back off. And we know that same thing right here. And we know the steel there's a force that helps steel getting longer, so we add a plus to it. By putting the numbers in this case 26 times 6 e to negative 6 times the changing temperature is 180 minus sigma of A 70 e to the 9. So P divided by A here becomes sigma of A. That's equal to sigma of A 0.21 times 200 times e to the 9 plus 117 e to the negative 6, 18. By solving the things right here, we know sigma of A, which is aluminum, is equal to 56.2275 times 10 to the 6 Pascal, which is equal to 56.2 megapascal in compression. So that's solve the problems. If you have any questions, feel free to leave in the comment sections, and I'll see you next time. quick intro about how the torque and the twist formula is derived from. So here we got our shear strengths due to torsions. Here's our rod. We have a torsion applied on a clockwise direction and counterclockwise directions. And we got our P go this way with our radius, and we got our twist angles when you twist it. So in this case, the arc length is going to be equals to P5, and that's the length times the shear strength. If we solve for the shear strength in this case, we'll get P5 divided by the L. And we know that the torque is equal to the shear strength times by G. Therefore, if we plug in the shear strength from the previous equations, we get P5 divided by length times G, that's equal to torque. And torque, the tension in this case, torque is equal to the integral of P, thing right here, and dA. So by solving for that, we have integral P squared dA. That's what we plug in. So from there, we're going to introduce an idea called the polar moments of inertia. And this is called J. And this is the integral of P squared dA. And if we plug in J instead of the P squared dA, we get G, our twist angle, J divided by length is equal to T. So by solving for our angle right here, we get TL divided by G and G. For the solid rod, J is divided by half pi C to the power 4. And when the rod is hollow, J is equal to half pi C of the outer radius to the power 4 minus C of the inner radius to the power 4. This is not equals to half pi C out minus C in to the power 4. When the tau, the torque, is max, how do we get that? Well, we know torque is equal to shear stress times G from the equations above, right here. Therefore, if we substitute in, we'll get the following. So we substitute in TL JG instead of the angle of twist right here. So that cancels out, but then we know that torque is equal to T times P divided by J. So when the torque is max, P is equal to C. Therefore, this whole thing becomes TC divided by J. And that marks the end of how we derive the J and our twist angle equations. But if you find this video helpful, please subscribe, and I'll see you next time. Hello everyone, welcome. Today, we're going to do problem 2, and the problem says for each of the 3 shafts, A, B, B, C, and C, D, determine the maximum shear stress in each of the 3 shafts. So, just a quick reminder, the maximum shear stress, tau maximum, is equal to TC divided by J. And J is equal to pi divided by 2 C to the power 4. So, by looking at this, what we're going to do first is cut the rod into 3 segments. So step 1, cut the rod into 3 segments. So the first segment we have is from A to B. So A and B, A to B, what we have is a 400 pounds inches going in the clockwise directions. So there's a T torque that counteracts the 400s, and let's say it is counterclockwise by our assumed directions. And we say if it's counterclockwise, it is positive. By summing up the torques, we have positive TAB minus 400 pounds inches. And we know that TAB, in this case, the torque, is equal to 400 pounds inches. Now, for this problem, it doesn't matter because all we need to know is the maximum shear stress, which you can just apply the 400 in this case. But it's good to know that we assume the 400 in the positive directions. The 400 is going to counterclockwise, which is positive. So that's our part for the cut of AB. And the second part we're going to cut is BCs. So what we're going to have is the graphic like this, where we got 400 pounds inches going in the clockwise directions. And we got 12 hundredths pounds per inches in the counterclockwise direction. And let's assume that the torque of the BCs, in this case, goes to the counterclockwise direction, which is positive. by summing up the torques, we have a negative 400s plus 1200s. Of course, our torque BC is equal to 0. We know torque BC is equal to 800, negative 800, which is 800 torque in the clockwise directions. So the last part we're going to cut is tension of CDs. So we got 3 parts as usual. We got 400s, we got 1200s, and based on the graph, we're going to have a 500 that goes this way. So it'll be 400, 1200, and 500. By continuing the directions we assume, let's say torque CD goes in the counterclockwise directions, we can say torque of T is equal to 0. So we got negative 400 in this case plus 1200s plus 500 and plus torque CD is going to equal 0. So